Hi everyone, this is Ayodhya, and today uh, we all are discussing about the reading assignment for my team members are Giridhar and Nanda. The first paper was discussing about learning the real-time A-star path planner for unarmed air vehicles. In this paper, discussed the path planner for sensing the target from fixed wings, fixing unarmed air vehicles. So the planner was created based on the real-time A-star search algorithm. So LRT A-star search of three procedures can use to find the path which has the minimal cost and the minimal length. Runtime and the path length are determined by the operating parameters of the LRT ESTA algorithm. If the targets are closed from the minimum turning radius of the vehicle, then path planning approach will be easy. But if the targets are too close, if we are using the traditional path planning algorithm, then it will we have to consider some other factors before we finally decide the optimal path. So path planning usually depending on two components, which is aircraft dynamics and the movement of the sensor footprints. The main objective of path planning is to optimize a path which lowest length and the lowest cost to reach the target. So let's take an example from the research paper. So here in this example, we will be able to see that starting point, and then we have three different targets to achieve. If we compare these three targets, we will be able to see that target 1 and 2 are too close to each other, but target 3 is like a little bit away from other two. So that means the planning will be starting from the in this if we are following the traditional approach, we will be planning the path from one starting point to the other point. For as example, if we start from the initial point, then we will be looking at only the next target point, which is this, and then we will be finding the path. Once we reach to the point A, then we decide which path we have to take to reach the target 2. So that is called a point-to-point or like traditional traditional way of finding the optimal paths. Here we have one diagram which will explain point-to-point optimal path plan. And the other side, you will be seeing that optimal multi-target path plan. So if you look at the diagram A, the optimal path is planned based on one target point to another target point. That means if the vehicle fly from the first target point to the point from the start, then look for the optimal path through second target point once it reached to the first target. So once the aircraft is reached to the second target, again it will be in a poor position to view the second target, because in this diagram we will see target 1 is a little higher position, target 2 is lower. So in order to get the correct path location, it has to be always a little bit over from the target point. So once the aircraft is reaching the second point, then again target 3 will be in a way like little bit higher. So yeah, we have to fly a little further or like go under to find out the correct location. If we are looking at diagram B, we can see path is determined based on the analyzing all three targets at once. So if we do so, when we are at the starting point, we will be aware of the what are the number of targets we have to achieve and the where it's located. So according to that, we can determine the best path to reach all three targets. So in the next diagram, we will be discussing optimal point-to-point path versus optimal plan utilization by using the footprints. So in the most aircraft has downward looking sensors such as OE videos or SAR or ladders. So they are capable of sensing the footprints of the significant size of the image. So if we are looking at the diagram A closely, we can see that path is determined without analyzing the sensor footprints. Hence, like when we start when we reach the like a target one, it had to make a big turn to come back to the target two and so on. In the diagram B, we can see that path is defined based on the sensor footprints. Hence, that the path provide an optimal solution. Another challenge we have is to determine which order we should travel. So task will determine traveling order, like traveling salesman problems, like we will be discussing later in this presentation, which is known by NP-hard. Apart from this example, must face the additional complexity. So here we discuss like some of the issues we have when we are determining the optimal path. But apart from that, then we have the issues identifying the correct location or the size of the target. So it is crucial when we are actually going for the optimal path utilization. The capabilities of effective path planning approaches. So by real-time A-star search path planner has been developed to meet all of the above requirements we have discussed, but plan optimal or near optimal path through the targets by overcoming the overcoming the limitations that have in the aircraft is something we have to pay much more attention when we are doing this. So utilize sensor footprint, fully weave the target and eliminate the needs to directly fly above the target approach. So if you remember the earlier diagram, I have mentioned that if we are going to point-to-point approach, we have to always be a little bit above from the target to see the destination, right? Path planning for robotic system has been drawn to significant attention these days. So most of the methods use the start point to point and ending point with the determining the algorithm. But in this paper is discussed on determining the path, knowing only the starting point and the number of targets that must visit. The next topic we will be discussing is probability and the probability road mapping. We called it as a PRM. In order to move between nodes, the algorithm needs to keep track of the control inputs required to move between nodes. An open loop control input sequence can be used to move from the start node to the goal node. So here, PRM randomly select the configuration from configuration space and the plan according to the local paths. After analyzing the path roadmap, it can be constructed based on the researchers or like previous information it has. The underlying idea of PRM is to find the probability of the optimal path, which path will converge to the one as the time spent building the roadmap goes to infinity. The related probability roadmaps are rapidly exploring random trees. So it is referred as RRT by random selecting points in the search space. So instead of like predetermining which points we have to go, we can use the tree space, the search space to understand which target we have to reach first and which is the correct order to visit all the targets with lowest cost. So the next topic is discrete step path. Discrete step path are built by assembling primitive turn and this straight segment from the flyable path. So if the algorithm produces a path that is not constrained by the endpoints or headings that utilize the full capabilities of the vehicle sensors and that satisfy the dynamic air control dynamics and the vehicles radius, like turning radius. So here in this example, we will be able to see um, uh, nodes are in the path in nodes in this path have the parent node. Every nodes in this path we have a parent node which is denoted by A here, and each node has the child node and we will be referred that as the letter C. So a set of the knowing targets can be referred by T in this algorithm, and in the above tree we can see the depth of the about algorithm about diagram we can see the depth as 3. So here we have the trust level, which is the most child level. The next we have the parent level, and here we have the parent of the parent, which is A. So we can say depth is 3. LRT A star tree search. In this search, the method applies to learn the real-time A star used to determine which branch of the identified path has the best accomplished to the desired path planning objective. So in here, like when we have the multiple paths to the reach targets, we can actually find the best path by using the tree algorithm. So you can use the below algorithm. So HC will be denoted as heuristic estimation of the child, and KC denotes the cost of the moving to the respective child. So one child to the other, the cost will be calculated by KC. So when we sub those two values together, we can finally find out the total cost to reach the destination. So next, we will be discussing initial heuristic value when the terminating conditions. So if in the heuristic value in LRT A star search, there are multiple problems are estimated based on the distance, and that must be traveled from the current node to the other node and the next node. The initial heuristic values are always be admissible, but they are not always close to the actual path length. Hence, each may convey slowly. So alternative heuristic values are used to find the distance to the target close to that vehicle, and then that distance, then the distance from that place to the target. Since paths terminations have two extreme ends, we must be able to combine it to create the terminating condition that encourage to continue the improvement. So that means, like if we are calculating path from point A to point B, there will be like multiple different ways we can take. So when we are doing running this algorithm, we will be comparing the cost or the metrics that we need to use to reach the destination. But if the metrics are not improving from one analyze to the second, then that will be our termination condition. After that, we will not be continue looking for the same path direction again. So we can start looking over for a different alternative approach. From here onwards, my team member will continue.
Thank you, Ayodhya. Now I'm going to discuss about the branch terminals testing and comparisons. And coming to the branch terminals, the performance of LRTS research is based on the memory management and pruning of the path tree. If the current branch is larger than the path, then the current node is killed by removing its children from the node and set the heuristic values to infinity, and the search is restarted from the root node of the tree. If the child nodes have the heuristic value as infinity, then the node is dead end. And path tree size. The main problem in searching the path tree is its size, because it takes more time to search the tree. The size of the full path tree is 3 power d, where d is the number of levels in the tree. There are two ways in decreasing the path size of the tree. One way to remove the size of the path tree is to remove branches that makes paths that often change directions. The search not be done for all nodes, because it takes a lot of time and use a lot of memory space to keep track of the nodes it has visited. In this research, LRTA start research is used. In this method, the nearest target is chosen as a source, and potential field algorithm gives a plan to reach the target. If it reaches the target, then it chooses the next nearest target and makes that as a source. This process continues till it meets all the targets. One advantage of LRTA star algorithm is that you can easily add new goals and constraints to the path. And coming to the testing and comparison, LRTA star and NILRTA star algorithms were tested on a set of 2,000 target scenarios. In each scenario, chosen a random starting point, target and a heading for the vehicle. With 512 MB of RAM and 1.33 gigahertz Athlon XP 1500 processor, Linux was used for the test. It took 1 minute for the algorithm to run, and data from yearly ending runs was used in the analysis. The NILRTS algorithm came to the end if it doesn't improve after 10,000 runs. Testing of this method has shown that a step size below zero point 0.2 radius have no meaningful impact on the algorithm path length. LRTA star research validation. Comparison based on the Dubin's root shows that LRTA star has more beneficial benefit than the brute force global searches. The figure A shows that the LRTA tree search comes close to producing the same minimum length path as the brute force global search, with the LRTA star path being only 0.5% longer than the brute force global search. Resetting the sensor to its original size made the path is shown in the figure B. This path is 33% shorter than one that has to go right over the targets. And coming to the path length, there is in figure 11 graph that shows how well the two algorithms work at different step sizes between 0.2 and 0.4 radians. The average path length grows by 6.8%, which shows that smaller step size become less useful. NILRTA performance is also shown in the figure. The LRTS performance, the NILRTA and LRTA performance is shown in the figure. At radian 0.2, the mean path length for the NILRTA star algorithms are 3.8% longer than those for the LRTA star algorithm, which is the same. For step size of 0.35 radians, and up the path length from two algorithms are the same for the same number of steps. It happens when you make a step size of 0.5 radians, the algorithm starts searching the full path tree instead of the simple path tree. The path length performance improves a little, but it doesn't make a big difference at the step size gets bigger. Mm, the LRTS star and NILRTS star algorithms as shown in these figures, with the average total running times for both algorithms at the different step sizes shown in each graph. at radians equal to 0.2. The average running time for LRTS star algorithm is 80 lakh nodes per 10 seconds, and for NILRTS star about 150,000 in 0.3 seconds. At radians 0.3, for LRTA nodes decreases to 2 lakhs, which is 0.98% decline. For NILRTA, the node drops to 80,000, which is about a 47% decline. The step size increases, then the running time decreases. For radians equal to 0.4, the algorithms are running similar. This graph B shows the average running times at which the best paths are found. Any extra running time is used to confirm the best path. For the LRTS star algorithm, about 85% of the time it takes to run its span, developing the best path is found. The NILRTS star spends about 93% of its running time running through the 10,000 times. It doesn't improve. Thus, if either algorithm is shut down early, the chances of finding the best path are very high, even if it was not. Results shown in the figure is that the running times for both of these algorithms go up as the number of target increases. Visit 5.5 million nodes for 8 targets, where are the NILRTS algorithm visits an average of 200K nodes for the same 8 targets on average. The NILRTA star algorithm is always faster than the LRTA star algorithm for any number of targets. As shown in the diagram B, the NILRTA algorithm has path length performance that is similar to that of the LRTA star algorithm. Now, my friend Nanda will continue. Thank you.
Hi, Udhi and Giri, and this is the second paper. Simple subgoaling for real-time search and constant and artificial intelligence control agents in video games must react quickly to players' commands. And coming to this, constant pursuits resolves the issue in a fundamentally count different way, rather than processing a total, possibly dynamic arrangement before the main move is to be made. And continuous pursuit calculations register a couple of first activities for the specialist to take. This is typically finished by directing a look ahead search of a decent profundity, or look ahead profundity around the specialist's present status, and utilizing a heuristic to choose the following scarcely any activities. The moves are then made, and the preparation execution cycle rehashes since the objective state is not come to by most such a neighborhood look. The specialist runs the dangers of heading into an impasse, or more by and large selecting sub-pair activities to resolve this issue. Ongoing heuristic inquiry calculations update their heuristic work with experience. Not only that, the learning system has blocked continuous heuristic search specialists from being generally sent for path finding in computer games. The issue is that such specialists tend to scour the state space due to the need to fill in the heuristic discouragements. As a result, the arrangement quality can be low, and outwardly the scoring conduct is seen as nonsensical. Okay, can I go to the next slide? Yeah. Yeah, despite we have seen in the figure one, click based abstraction employed by DLRTA star, and various scientists have endeavored to accelerate the learning system. Approaches differed from the backtracking and to heuristic weighting, to focused on clearing, and to state deliberation, to various updates per activity. And several scientists are worked on this, and as per the years it is shown in the years as per the years who worked according to it. And be that as it made, the best exhibition was accomplished by practically disposing of the learning system. This should be possibly by registering heuristic as for a close by sub goal rather than a far off objective. Since heuristic spam works normally loosen up the issue, and overlooks impediments on a guide. They tend to be more exact, more like an object. Subsequently, a heuristic work as for a closed by objective will be in general be a lot more precisely, and in this way requires little change. And yeah, coming to the sub-goal database constructions, we can see in the figure 2, sub-goals are defined by using the DLRTA star, and S is the agent state, and G is the global goal, and capital G is the global goal, and small g is the sub-goal. And our inspiration is to hold DLRTA star amazing execution while working on the calculation and the loosening up memory requirements. The most memory consuming piece of DLRTA star lies with its sub-goal dataset. To construct the dataset, DLRTA star first digests the guide utilizing the faction deliberation plan of PRA star. And the figure 1 outlines the cycle. A matrix based map is changed over a chart, and the B which is then preoccupied so that each inner scale of unique states turns into a solitary conceptual state. When the deliberation is finished, a ground level state is nearest to the centroid of a club is picked as a representative for the theoretical state. We set off to think of a less difficult approach to building a sub-goal information base. Thus, our methodology depends on the following thought: the least difficult and quickest form of constant. Such calculations are LRTS star with a look ahead of 1. Such a nearsighted LRTS star is basic slope climbing augmented with a Bellman update rule for the heuristic. Yeah, and coming to the compute sub goals, and here is the figure 3. Sub goals are as defined with K and N, LRTS star. First thing is we need to load the map for N equal to 1 up to so on N do, and to generate and then generate a random pair of states S start and S goal. Compute an optimal path P from S star to S goal with A star. If P equal to pi V uh, P greater than 3, then go to step 3, and if for I equal to 3 up to so on P do. If Si is not a hill climbing reachable from S start, then store sigma n equal to S start S goal Si minus 1 Si to 1 in the sub goal database. Break out of the inner for loop end if n for and n for again, and the resulting algorithm constitutes the offline database building of KNN star. We take a map and a desired number of goals n. We then generate random pairs of ground level states which are reachable from each other, or at least movable parts. We run a star for each pair to compute an optimal path P between the pair states. We then go through states for each SIs. We check if it is reachable from S starts by using simple hill climbing with the heuristic computed with respect to SI line 7. And the sub goal for S start and S goal is defined as the fastest state on the path P, which is hill climbing reachable from the S start. Then N records if the sub goal database sigma are of the form S start, S goal, and S sub goal. It is shown in the line 8. And coming to the next slide, and the runtime search, processing a sub goal for each pair of states is optionated for any inconsequential guide. Subsequently, often the state of the specialist and its objective won't be in the information base of sub-objectives, that the specialist cannot investigate its accurate objective, yet should sum up from the accessible records. And one broadly utilized but then basic component for runtime speculation is K closest neighbors, and the thought lies with the kind of finding K closest cases to the main concern, consolidating their pre-computed answers and involving the blend as an arrangement. We apply the methodology for sub-goal determination, and for this simplicity set K equal to 1. Consequently, at whatever point a specialist is in the states S start, what's more, will state yes goal if it checks the sub goal information based on the track down the most comparative record. It is shown in the line in the figure 7, line 4 in the figure 7, and the similitude is characterized as the number of the heuristic distances among S start and S star start, and among the S goal and the S star goal, as shown in the figure 5. The heuristic distance on maps is commonly a procedurally indicated capacity like Euclidean distance, Manhattan distance, or the Auckland distance. Speculation of Manhattan distance to the inclining activities. These distances discrete map returns. When the specialist finds the data set record generally comparable to its present circumstance, it sets the subgoals and the subgoals from that record similar to possess subgoal and continues towards it utilizing the standard LRTS star and the lines 8 and 12 in the pseudocode as it is shown lines 8 and 12. And coming to the properties, to limit negative indications of the subsequent learning process, we run LRTS star with more profound look ahead, which is known to diminish learning. Second, we can be proactive by expanding the number of records in the dataset, trying to increment comparability between specialist circumstance and the nearest coordinating record in the dataset. The third issue lies with the potential cycles. It can so occur that the specialist arrives as its picked subgoals, and afterwards sets the following subgoal, which brings it back. And in the wake of coming to to that subgoal, it might wind up choosing as subgoals again these lines entering an endless circle. And we address this issue by fundamentally tying an untouchable rundown T of the subgoals utilized by the specialist on an issue. Therefore, no subgoal can be chosen two times. And fourth, on the grounds that our closeness metric depends on the octal distance, it discretes obstruction. Subsequently, the most similar record might turn out to be on the opposite side of an obstacle, making the specialist invest a ton of energy working its way around the snag. We reduce this by checking if a start is slope climbing reachable structure S start, and on the off chance the S star goal is slope climbing researchable structure goal as shown in the line 5. If they are not, then at that point we go on to the second most comparative record the data in the data, etc. Yeah, this is shown in the next best in the line 6. If all the records are depleted, the specialist defaults to the worldwide objectives. Notice that we use the slope climbing reachably checks to the manage issues 1 and 4 to fulfill the genuine time imperative and keep such checks from talking longer as the guide explains expansions in size. We limit all slope climbing checks to a steady number of steps m as displayed in line 3 and 5. And okay, and then yeah, thank you each and everyone.